Okay, so let's get going for today. Today we're going to be talking a bit about stacking to average posterior predictive distributions, but we're also going to be talking about a bunch of other things pertaining to Stan, in which case we first have to talk about the fact that because Columbia seeks grants to develop Stan, I develop Stan, I use Stan outside of Columbia, that creates the appearance of a conflict of interest that you should be aware about. Also, we crunched the numbers last week, actually lost 5Gs last year, so I think that should make it even more something. Mostly because I was paying another guy to do some data collection stuff that Columbia doesn't pay very much, so. Anyway, been contrasting different approaches to applying quantitative methods, whether that's in the social sciences or not, but particularly when you're trying to apply quantitative methods to the social sciences or anything having to do with people, it seems to me the Bayesian approach is the most appropriate one, and the one we're talking about this semester is really sort of the minimum you need to know in order to apply Bayesian methods to social science problems, but it's not the one that programs overall spend the most time teaching. So the one that probably is taught the most throughout Columbia and historically has been the frequentist approach, which is to solve some optimization problem using an entire sample of data that has been randomly selected from some population, and then use the language, use the tools of probability to describe the probability distribution of the optima across data sets that have been sampled from the same population as the one data set you have. And when doing those descriptions in terms of probability distributions, all of those are conditional on the true parameters theta that you don't know. Also, all the probability statements are pre-data statements. And so everything, the standard errors, well, that is, or the estimated standard errors, the true standard errors are the sampling distribution of the optima if we were able to collect many, many data sets of size and solve the optimization problem many, many times such that we have this probability distribution of optima, and that's usually going to be a normal distribution, but again, this is describing the distribution of the estimator across data sets, and then p-values as a tail probability of some statistic conditional on null hypothesis of some sort being true. Often that some coefficient is 0, and so p-value gives you the probability that in another data set, when you do the optimization, you overestimate the parameter even worse than you did in the present data set, but conditional on the true parameter that you're trying to estimate being 0. And confidence intervals is sort of a range of values such that if your null hypothesis were anywhere in that range, you would fail to reject the null hypothesis. Now, I think all of these questions that you can give probability answers to in the frequentist paradigm are sort of weird questions that don't seem to be that relevant for the practice of social science or much anything else, particularly industry applications, etc. But it is possible to do this in a very coherent way, and it's been done. It wasn't entirely done by Fisher in the 1920s, but certainly set the foundation for that, and it's pretty well understood. Properties of these or asymptotic properties of these sampling distributions across data sets, such that I can't really remember what was the last time there was a big innovation in frequentist thought maybe like bootstrapping in the 1970s, but it's mostly just a solved problem for the most part, although people still come up with new estimators and have to work out what the distributions of those things are. Now, it's a little bit different between economics and statistics. In statistics, you're going to be maximizing a likelihood function and then thinking about the distribution of those. In econometrics, it's more common to see people minimizing the distance between sample moments and population moments under the model, but that distinction doesn't matter too much. If you're solving an optimization problem, you're solving an optimization problem. And if you're using probability to describe what would be the distribution of those optima across data sets, then you're a frequentist. In contrast, the supervised learning approach, which has been influential recently within statistics departments, certainly out there on the internet, but is being pushed by a lot more computer science, engineering, those sorts of departments than just traditional statistics departments, is, well, we're going to solve an optimization problem in the training set of data and then use the prediction point estimates that we get from solving that optimization problem in the training data to predict the outcome in the testing data, and then see which of the various models that we can do is going to predict best in the testing data. And so, like the frequentist approach, they're solving an optimization problem, but a much departure from the frequentist approach. They're not using probability to describe the distribution of the estimates obtained across data sets, because they find that not interesting, particularly in industrial settings where they don't care at all about what the distribution of some estimator would be in data sets they don't have, not even interested about the parameters in and of themselves anyway, so not interested in testing a null hypothesis that some coefficient is 0, only interested in what the estimated coefficients imply for predicting future observables. And if you take that approach, which, as I tried to emphasize last week, is doing a lot less than what statistics traditionally does, frequentist statistics traditionally does, then you're not worried about getting like the sampling distribution of some statistic across data sets, then you're free to start changing the objective function that you're optimizing to make it more suitable for your tasks. So adding on these penalty functions that penalize implausible values, are to the increasing penalty as you get more and more implausible values of those parameters. And that tends to work best for this purpose, which is to predict the outcome in the testing data. But the reason why these sorts of things weren't traditionally being done with the frequentist approach is it's always one of like 4 reasons. Like if we add penalty functions, then we can't solve the optimization problem. Or if we can't solve the optimization problem, more relevant, if we add penalty functions, then we can't derive the distribution of the test statistic under the null. Or maybe we can still derive it asymptotically, but the size of the sample you need n in order to make that asymptotic distribution be at all relevant to the size of the data set that people are actually collecting might be implausibly large. Or finally, if all other reasons fail, it's because we can't interpret the estimates that come out. But if you sort of take the supervised learning approach, none of those questions matter. There's no real interpretation or testing or anything like that going on. There's just prediction of the outcome in the testing data. And so they're sort of changing the function being optimized in order to be more suitable for the task they're interested in, whereas these likelihood functions that statisticians were maximizing are more suitable if your ultimate goal is to derive like the distribution of the estimated coefficients across data sets and test some null hypothesis about a coefficient being 0. The Bayesian approach is starkly different from either of those two because rather than solving an optimization problem, we're solving, or at least posing, an integration problem. Solve an integral to get the denominator of Bayes' rule, the marginal probability of the entire data set that you have. But in practice, like, we're never really, in that many situations, able to solve that integral analytically. So instead, obtain draws from the posterior distribution of the parameters conditional on the data that you have, and then use the language and the tools of probability to describe any function of those unknowns, including prediction of future observables. But all of that probability stuff is for the unknowns or functions of the unknowns, conditional on the data that you've observed. And there's no, what if we were to obtain another sample of size n? That's all irrelevant, not being used in the probability calculations or in the estimation or anything like that. And so Bayesian inference is sort of exact for the data set that you have. No, like, what if n goes to infinity? None of that is necessary to justify Bayesian inference. Indeed, you don't have to make any distinction between sample and population. It's just like, I have some data, it may or may not be a random sample from any population, and here are my beliefs after seeing the data for the parameters that were in the data generating process for that data. Now, you can think of the posterior PDF as the solution to an optimization problem, namely, what is the function that is closest to the prior PDF, subject to a constraint implied by the data. And so you can think of the posterior PDF as a solution to an optimization problem, but it's a very different optimization problem. It's a question of choosing the optimal function rather than what the frequentists are doing in the supervised learning people, which is to choose optimal points that maximize some function. Now, that's sort of the way I see it. I recognize that that sort of description of these sorts of things into the three categories of people omits some other less common approaches that people take, but those less common approaches also tend to entail solving an optimization problem. And so they're pretty close to either the frequentist or the supervised learning thing. There's also, considerable variation, or at least there was, between Fisher versus like Neyman and Pearson and their approach to frequentist inference. There's also a bit of heterogeneity among, the supervised learning camp. I suppose a less cynical way to define what supervised learning is trying to do is not, well, they're the branch that just does optimization but that just like ignores all their uncertainty. A less cynical way would be to say, well, supervised learning is more interested in estimating the functional form of these conditional prediction functions. And so in contrast to frequentists and even some earlier Bayesian stuff that just tended to assume like linear functional forms or generalized linear functional forms. But I don't think that is a distinction that is particularly useful because it's not inherent to supervised learning. It doesn't mean frequentist people couldn't use nonlinear functions, or Bayesian people couldn't or aren't using nonlinear functions. It's just a question of emphasis and what can be solved. So some of those things are sort of more difficult in the frequentist thing to relax these linearity assumptions. It's pretty easy with the Bayesian approach, but you have to have something as powerful as Stan to go about estimating that and to know when you're not estimating it correct. So there's an entire branch of Bayesian approach called Bayesian nonparametrics, which is a stupid name because there's actually an infinite number of parameters in those that overlaps more with a lot of the fairly advanced supervised learning things. But you can always tell a genuinely Bayesian approach by like, is there a posterior distribution? Do you have draws from it? If you only have 1 point, it's not Bayesian, even if the person like says it is. So questions about some of those distinctions? Yes, Devon.
More than about the specific distinctions. A few weeks ago, we were talking about how with extremely large data sets like Google's and so on, Bayesian might not be necessarily necessary because there's so many observations that you can just get a data, like a precise estimation. And then we were saying it, however, when you start maybe modeling at a hierarchical level under different populations, you might use Bayesian for those subgroups. My question is, however, in the homework that we did, I saw that Stan struggles, let's say, when you get a lot of draws for even a relatively small number of data points. And I was wondering how that applies to such big data sets as Google, and if Stan can handle the simulation, let's say, of such big data sets.
So there can definitely be computational problems in practice with obtaining draws from a posterior distribution. And those can come from, a lot of different ways. So if you truly had a data set like the size of Google, you might not be able to load it into memory. So that's one of the, aspects about Stan that's not ideal, is that all the data are loaded into memory. And if you're doing like 4 chains simultaneously, all the data are loaded into memory at least 4 times. And so that can make it difficult, whereas in other situations, like SAS and SPSS and some of the other things, can keep like 99% of the data on the disk and just load in like 1% of the data at a time into memory, like do some stuff on it, then get another 1% off the disk into memory and put the other one back. And that enables you to obtain like a solution to some problems for data sets that are too big to fit into RAM. So that's one thing. But even before you get into like that, big a data set. So let's say a data set that just barely fits into the RAM that you have. Well, that posterior distribution may entail that Stan has to take steps that are so small because the curvature of the posterior distribution is so rapid, the second derivatives are changing, that the first order approximation being used by Hamiltonian Monte Carlo is only a reasonable approximation for very small steps. And if you take very small steps, you may have to take many steps before no U-turn sampling reaches the U-turn point and turns around. And so if you have to take many small steps, that means evaluating your log posterior kernel many times. And if your log likelihood is summing up contributions from billions of data points, each one of those function evaluations takes a relatively long time, like half a second or something like that. But if you have to evaluate your function like 1,000,000 times, now you're talking about like 500,000 seconds to complete. And so those are challenges, but they're mostly sort of computer science engineering challenges as opposed to conceptual ones or statistical ones. What a lot of these approximations that you see these days that are intended to be first and foremost fast is one, there's no great understanding or even a whole lot of caring on the part of a lot of people as to how good these approximations are. But there's sort of a lot of approximations out there that are like, assume the posterior distribution is approximately normal. Now, can we do something that's faster than just like full-blown general no U-turn sampling sort of thing. And those I find irritating, because if the posterior distribution were close to normal, multivariate normal really in multiple dimension, Stan is just going to eat that up. It's very efficient on posterior distributions that are approximately normal. Now, if you have a billion data points, like, it has to evaluate a likelihood function that is like, super complex. And if you have, a complexity that's like polynomial in n, then, it's going to take a while. But Stan is actually like very, very efficient for posterior distributions that are approximately multivariate normal. And so the idea is, well, let's like assume for no particular reason that it's multivariate normal and do something fast, ignores the fact that Stan is already like very efficient for those sorts of things. So if you're really gaining like a hugely observable difference in speed between like whatever your fast approximation thing does and what Stan does, then it's presumably the case that the posterior distribution that you've defined isn't actually that close to a multivariate normal. And that's why Stan is like slowing down, taking the small steps, etc. So those things are out there, but just like in terms of a rant or in terms of like what you should be conceptualizing, I think these are the important points. And then the question of, okay, well, once I've picked an approach, which I think in the social sciences would ordinarily be the Bayesian one, like, how can I achieve it? And that is really, the fact that these integrals that you sort of needed to solve were impossible is one of the things why Bayesian methods, or why frequentist methods really got a head start, starting in like, I don't know, a generic optimization, minimize a function, that was mostly figured out in like by 1970. So just like, here's a likelihood function, I can't solve it analytically for the mode, just like numerically climb to the top of the hill and stuff. They knew how to do that in like 1970. So that gave the frequentist approach, like in terms of when social science started, coming into more prominence, a lot of a head start, and it was in the textbooks and all sorts of things like that. The Bayesian thing didn't really get started until the mid-1990s, and even then it was like extremely slow and only worked for like not that many models. But sort of the same thing with supervised learning, they already had like well-established, for the most part, numerical means for finding these optima, and then it's just like thousands or millions of papers that are just like, here's a slightly different optimization problem, but I already have a library to solve it. It really, in my opinion, wasn't until Stan got off the ground that you could really think about doing Bayesian inference with the sort of generality of problems that you can apply it to that you see with frequentist approach and some supervised learning stuff. So we're still catching up, but Stan really was an extraordinarily important leap forward that is, put into place by a bunch of people, but in particular Matt Hoffman for coming up with the no U-turn sampling algorithm, the original version of it. So these different perspectives on applying quantitative methods involve sort of different perspectives on the role and the way in which you do prediction. So you can do prediction in the frequentist sense, but it's very weird. It's like, what is the distribution of predictions across data sets? Whereas usually someone like who, has a real job or something like that is sort of saying, well, I'm going to get more data next week, but I want to predict what that data is going to be like this week. It's not, what if I were to get like 100 data sets and then obtain 100 maximum likelihood estimates and obtain the prediction for next week across those 100 data sets and then get this distribution of predictions that's implied by my sampling distribution of the estimator. And so the frequentists, even the proponents of frequentists, have never really emphasized prediction as that important a task as compared to estimating the parameters. It certainly is from a supervised learning perspective, even though what I consider to be the bulk of supervised learning is just completely ignoring all the uncertainty in those predictions, and as a consequence, it's not very good for making decisions. You can also get predictions from a Bayesian model, and you actually get a distribution of those that you can, put into a utility function and then maximize the expectation of over your space of decisions. But just, let's focus on the task of like, how can we get good predictions? The first thing that you want to ask yourself is, do you want a model that is expected to predict future data well, or a model that actually predicts well in the testing set? And if you just like put that question on Stack Overflow or something like that, 99% at least of the responses would be, well, you would want a model that actually predicts well on held out testing data. And that is the wrong answer, but it's a wrong answer that seems obviously right to the vast majority of people who are doing quantitative methods. And so we want to think carefully as to why that is, because no one actually cares about how a model does on the testing set per se. The testing set, if you've collected it by definition, is past data. What you want to know is how well is the model going to work on future data, but you're using your held out testing data set as a proxy for future data because you haven't used the testing data in the process to obtain your estimates of the coefficients that you then use to obtain predictions. Whereas, with the Bayesian approach, you can condition on all the data and then obtain the expectation of the predictive density of future data. So if I ask the question the other way around, do you want a model that works well across all possible future data sets, weighted by the probability of those future data sets transpiring? Or do you want a model that works well on one particular realization of the data in the past that, for all we know, you may have played around with in order to like get the results that you want or whatever? So I'm sure it happens all the time that people split their data into training and testing. They run something on the training data, they get results that they don't like for whatever reason, and then they split the data into training, or split the original data into training and testing in some other way, just randomly split it differently, 75%, 25%, do it again, and then maybe the second time you get the results that you were looking for. That's a sort of supervised learning version of p-hacking that has been such in the news for problems with frequentist statistics. But even if you don't like cheat, and it's not even clear that that's cheating because it's not even totally clear what would be the right or wrong answer from a supervised learning perspective. But at best, you're just getting this works better than everything else on one realization of testing data, as opposed to all possible realizations of future data weighted by the probability that they transpire. And if you look at it that way, actually remembering what the definition of the expectation is, as opposed to what expect tends to mean in English, whereas like in English, your expectations are sort of never satisfied. But with statistics, expectation means a different thing. And that's something that you really should care about. You're averaging over all possible future data sets with weights that are implied as to what your model is predicting for those data sets to occur. Also, Bayesians tend to use log predictive density, other things that are known as proper scoring rules. So a proper scoring rule is one where utility is maximized if the predictor is being honest. Non-proper scoring rules, which are often used by non-Bayesians, can actually have their utility maximized when the person doing the predictor is lying. Person doing the prediction is lying. And Frank Harrell has a nice post in his blog about all the damage that can and has been done by using non-proper scoring rules, particularly in the field of pharmacokinetics and other things related to the FDA, where Frank is advisor now. So we want a utility function for future outcomes for Bayesians. The one that tends to be used as the logarithm of the density function of future outcomes conditional on past outcomes, which is a proper scoring rule. And so that's one of the main reasons why it tends to be used by Bayesians. But we're going to, estimate and approximate what those future outcomes are going to be by predicting observations that we already have. But we want to change our posterior distribution. So rather than making the predictions for each observation that we have conditional on all the observations, we want to make the predictions for the ith observation be conditional on all but the ith observation. And so that can be accomplished doing leave one out cross-validation, where you estimate the posterior n different posterior distributions, each one leaving out one observation, but then you would have to run stan n times, be very computationally demanding, and something would probably go wrong at least once. And so instead, we can estimate either very well or knowing when the estimation breaks down, what would happen if we were to do what I call literal leave one out cross-validation by only estimating the model once, using all the data, and then using a reweighting scheme n times to come up with what the posterior distribution would look like if we were to leave out the ith observation, using Pareto smooth importance sampling. And the Pareto smooth part of that is intended to reduce the noise that tends to occur in other important sampling schemes. And this one works very well if you could leave out the ith observation and it would only have a small effect on the posterior distribution. Small differences are things that we can bridge with reweighting. If leaving out the 17th observation would have a big effect on the posterior distribution, we might not be able to accomplish what we need to do just with reweighting, in which case you'll get a very high estimate of the Pareto shape parameter k when you do that. And Lou will give you a warning saying, like, the 17th observation had a Pareto k that was too high. We suggest doing this, and it will re-estimate the model once, leaving out the 17th observation, obtaining that posterior distribution, and then predicting the 17th observation, and then combining it with the Lou CV, or Pareto smooth importance sampling estimates for all the other observations. And so you may have to estimate your model like twice, but you don't have to estimate your model n times, provided this assumption about the Pareto k-hats being small is satisfied. And then once we've established that, which was we were trying to do last week, but it's important enough to spend some time doing it this week, just to reemphasize that you can do a lot of stuff with these leave one out predictions. You can do it for model diagnostics, for model comparisons, and other things that we're going to talk more about today, and also in future weeks, and also other things that aren't really on the syllabus but also are important, like if you're doing this with time series models and things like that. So are there any questions about this idea of leave one out cross-validation as sort of a way to get at the expectation of the log predicted density of future data, or the approximation to literal leave one out CV, which is done by estimating the model once and then reweighting it n times, where the weights are the function of the likelihood, or about the assumption of small Pareto shape parameters in the Pareto smooth part that is necessary for this estimator of literal leave one out cross-validation to be a valid estimate. Questions about any of those? But the upshot of it is that you can get at the expected log predictive density just by estimating your model once. or just by obtaining the posterior distribution of your model once. This obviously only works for Bayesian approaches. They give you a posterior distribution. And so that is what we're going for here from a predictive. Questions about that? So just to pick up again, some models for voting preference in the year 2000, when the election was between George W. Bush and Al Gore. So we take this data set, filter it down to the year 2000, make income a factor, which is how it was coded in this national election study data, and then change age from years to decades in order to estimate a coefficient that's a little bit farther away from 0. We have just a linear model where the probability of voting for Bush over Al Gore is a function of the age, the income, and the race of the person. So we just estimate that model. We can estimate a quadratic model by adding age squared to the original model. We could have just specified it from scratch, but we can also use the update function, which takes a previously estimated stand model, and you can change some of the arguments. Although formula has a period in the argument name for weird reasons. But anyway, what this means is use everything that was in the original formula except add on h squared as a predictor. And so now we're estimating a quadratic model, or a model that's quadratic for the log odds. There's always this nonlinear transformation between the linear predictor and the conditional expectation, which is the probability of y being equal to 1. And we're using the logit link function, or inverse logit, inverse link function, to map from log odds to probability. Could have used the normal, in which case we get a probit model. Could have used, something that has heavier tails, in which case, that might be an interesting model to estimate as well. You can compare logit versus probit versus, some other form of the inverse link function using the tools that we've been talking about last week and this week, and especially today. So we've got a linear model in the log odds is linear as a function of those. We have a quadratic model where the log odds is a quadratic function of age and also has income and race. And then we can also estimate a model that makes no particular assumption about the functional form by which age relates to the log odds of voting, except that it is some smooth function. And that smooth function can be approximated by the sum of a fairly large number of basis functions, each of which has its own coefficient that we can be estimating along with the coefficients on income and race. You do have to bump up adapt delta in that situation in order to make the divergent transitions go away. But it's a model that is, fairly easily estimated by Stan. It's also one of these models, particularly not the MGCV version, but the GAM version that is maintained by Trevor Hastie and maybe some of his colleagues at Stanford. This idea of, let's estimate some smooth function is something that is very common in supervised learning. But I don't think it's sort of intrinsic to supervised learning. Even if you didn't care about predictions about future elections, you could, if you wanted to, estimate a smooth function of age to tell you something about the dynamics of voter preferences in a past election, like the one in 2000. So this idea of using smooth functions rather than just assuming everything is linear is possible if you don't need to sort of test a null hypothesis that age is irrelevant. But both the supervised learning and the Bayesian approach are able to do that fairly easily. And with the Bayesian approach, we get full uncertainty estimates. So estimate those things. Call Lou on any of them. This is on the linear version of the model, and we get these three things here. ELPD is negative 574. That means nothing in absolute terms. It's only relevant when being compared to some other model that is being estimated on the same data. So exactly what number you get here, it depends on how many observations you have and like all other sorts of particularities about the posterior distribution that you estimated. So that the absolute units here are just nothing. They don't mean anything at all. But in relative terms, for another model that's different, estimated on the same data, and then you subtract one for the other, all that washes out, and you get a good means, a good way of comparing whether one model is expected to predict future data better than another. And so we can put this up for the quadratic and the smooth model and just sort of eyeball things. But first I want to clarify some more stuff about what is going on here and how this relates to other things that you're going to see out there in the literature. So expected log predictive density, that is kind of a mouthful, but we know sort of exactly what that is. The expectation, it's an expectation over future outcomes of the predictive density of future outcomes given past outcomes, and for that you have to draw from the posterior predictive distribution, integrate out the parameters. But anyway, that's what Bayesians are going for, and certainly that's something that seems sort of intuitively correct, even if you're not too like caught up in the distinction paradigms that people are using. And so we can estimate the expected log predictive density with any draws from the posterior distribution. It doesn't necessarily have to be stand. But if you can get some good draws from any posterior distribution, you can plug them into loop, estimate the expected log predictive density, and that's going to go pretty well if the Pareto K values are small, and if the Pareto K values are not small, you'll get warnings about it, and so you know that, okay, I'm going to have to re-estimate my model a few times doing literal leave one out cross-validation, but I don't have to do it n times. So that's what ELPD is. Blue IC is just -2 times ELPD. So if you look at this here, if you multiply 573.7 by, or -573.7 by -2, you get exactly 1147.4. So that has no additional information. It's just changed the units. To change the units to be comparable to other information criteria that people have been using for a long time in order to do model selection. So all this AIC, DIC, WAC stuff, those are all in the same units as LUIC, which is -2 times the ELPD. And all these other AIC, DIC, WAIC are all ways of sort of indirectly getting at something that's proportional to the expected log predictive density. But if you've heard about some of these AIC things before, it was always, well, choose the model that has the smallest AIC. Okay, that's fine. But with what we're doing, we're tending to prefer the model that has the highest ELPD. And so in order for that to make sense, we have to multiply ELPD by -2, and now we want to choose the model that has the smallest LUIC. But that's really just changing the units in order to be comparable to the units being used by, frankly, inferior approaches to model comparison in terms of predictive accuracy. Now, the WAIC has gotten popular. It's about as good as LUIC most of the time, but or at least when the Pareto K values are small, then WAIC and LUIC are basically going to be the same thing. But with the Pareto K stuff, it gives us better diagnostics as to when the assumptions of LUIC and WAIC are not being satisfied. And if you just did WAIC without any of the Pareto smoothing stuff, you would get this number, but you wouldn't know whether, you know, leaving out this or that observation would have a big effect or a small effect on the posterior distribution. So you don't have this automatic, more or less automatic way of diagnosing when the assumptions which are common to WAIC and LUIC are being met. And so it's preferable to just do LUIC with the Pareto smoothing, and if it gives you warnings, make sure to heed those. So WAIC is like no better than LUIC, and then sometimes it's worse, and even when they're both bad, you can tell from LUIC, and you can't tell as easily from WAIC. But WAIC is a lot better than the deviance information criterion, which was popularized by Winbugs starting around 2000 or so, which is in general worse, or on average worse, but it's about as good as WAIC when the posterior distribution is close to multivariate normal. But again, not only is it sort of not telling you when, you know, one observation has an influential effect on the posterior distribution, the deviance information criterion doesn't tell you anything about whether your posterior distribution is close to multivariate normal. It just assumes that it does and then estimates the deviance, and that's, you know, negative half of that is the estimate of the log predicted density. So don't use DIC, LUIC is much better. But even the DIC is better than the AIC, which has been around for the longest period of time and is used by a lot of people, both from a frequentist perspective and from a supervised learning perspective, even though I don't know that it really makes that much sense from either of those. But anyway, it's about as good as the deviance information criterion, in addition to the posterior distribution being, you know, approximately multivariate normal, when the priors are improper or otherwise not influential at all on those posterior distribution, and the AIC doesn't tell you whether that assumption is satisfied. So the best estimator of the ELPD, and the one that is the most you know, weakest assumptions, and the one where the assumptions that it does make are, you know, verifiable after the fact, is just doing glue to estimate the ELPD. Everything else is a slightly worse or much worse way of trying to estimate the same thing with less robustness and less ability to diagnose when something goes wrong. But none of these work particularly well when you're comparing more than like a handful of models. Exactly what I mean by handful is sort of hard to quantify. It depends on how many observations you have. It depends on how complicated those models are. But it's not real good for doing what a lot of supervised learning people tend to do, which is to just run off like 100 different ways of training a model on the training data and then seeing which one picks best in the testing data. Taking that approach and just say, oh, I'm going to do ELPD in order to score these isn't that good, because when you're doing sort of a lot of models relative to the observations that you have, then the bias, which is usually pretty negligible when you're comparing like a small number of models, starts to creep up. And even if the bias wasn't that severe, the variance would also get, you know, big as well. And so these are more intended for sort of comparing a handful of models. Approach for sort of selecting a particular model within a larger model that includes tons of predictors, we will talk about on Thursday. Different R package. Anyway, questions about these other information criteria and how they relate to the one that we are emphasizing in this course, mainly the ELPD? Good. So now on to like the reading for today. So in the supervised learning literature, actually kind of before supervised learning became that prominent, there was this idea of stacking, which is, okay, let's estimate each of the models n times. And remember, we could be estimating like 100 different models or more than that. Each time leaving out the ith observation. So do sort of literal leave one out for all the candidate models that you're considering. And then after you've done all that for all the different models, choose weights and that can be applied to the predictions from each of your candidate models in order to minimize the weighted squared prediction error in the testing data. So if we have like, let's say 5 models that we're considering, we need 5 weights that are positive, add up to 1, and the sort of weighted sum of the predictions, how can we choose those weights in order to minimize the squared prediction error in the testing data? So that sounds like a reasonable enough approach if you've already bought into the supervised learning thing. So rather than making a prediction from just one model, use all of your models, but give them the appropriate amount of weights. But how do you choose those weights? Well, it's something that was actually worked out, but the key problem is that you just have point predictions from each of your candidate models, and those don't reflect or those ignore all of the uncertainty that probably should have been propagated through to the predictions, and as a result, you know, this might not work so great, or even if it does, you have no sense of the uncertainty around those predictions. And you know, for one reason or another, this isn't actually used that much in the supervised learning literature, even though you know the idea has been floating around for a while. It's much more common to just, you know, you have like 5 candidate models or maybe 500 candidate models, and you know split it into training and testing, train all of them on the training data, see how well they predict the outcome in the testing data, and one of those is invariably going to work a little bit better than all the rest, and you just sort of take that one and go with it, ignoring the possibility that you know the reason why that one came out on top as opposed to the other one was just a function of how you randomly split the training data into training and testing, or some other quirk that probably is not going to be, you know, represented by future data, but some quirk about the past data. And so, you know, just see which one is better than the rest and go with that one model is, you know, what you see almost always these days. But you don't have to do it that way. You could do some sort of weighted sum of the predictions across all the models. And that's really what we want to do from a Bayesian approach, which is choose the weights over the candidate models, so non-negative, adding to 1, in order to maximize the expected log predicted density of future data where you're estimating this expected log predicted density for each of your models using the Pareto smooth importance sampling estimation of leave one out cross-validation. And the reading for today by Yuling Yao and Aki and Andrew Gelman and Dan Simpson and maybe some other people shows how to do that. And if you want more details, you can ask Yuling. He's a PhD student in statistics at Columbia. Anyway, it shows how to do that, but you don't really need to know how. You just need to know how to type in the thing in the loop package, which does this. So if you have 3 or more or 2 or more stan models that were estimated by the functions in rStanArm, you can put them together in this thing called the stanreg list. So this just makes like a list of models estimated by rStanArm, pass it to the Lu model weights function, and you get back the optimal weights for the 3 models that are expected to maximize the log predicted density of future data. And in this particular case, like 1% of the weight got put on the linear model, and the rest pretty much got put on the smooth model. So in this case, like pretty much nothing would be lost by ignoring the first two and just going with the third, which is like what supervised learning typically does, but they typically don't get these weights that say like one model was, you know, sort of overwhelmingly more important for the predictions. They just sort of see which one is slightly better and go with that. Now, if you look at, oh, I put Lou up for the linear model. If you did this for the quadratic one, it'd be a little bit worse. And if you did it for the smooth model, it'd be a little bit better. But in terms of like choosing these weights, sometimes what you'll see is like if you're estimating a few different models and like one is nested within the other. So the linear model is nested within the quadratic model if you just put a 0 on the coefficient on the quadratic term of age. And both of those linear and the quadratic models are sort of nested within the smooth model because both a linear function and a quadratic function are particular smooth functions, but the stand GAM4 was capable of estimating almost any smooth function. And so sometimes, and in this case you do see that when some of the candidate models are nested within a more general model, and the more general model is like a little bit better, it puts almost all the weight on the more general model when you do this thing here in order to obtain optimal weights to maximize the expected log predicted density across the candidate models in terms of predicting future data. Now, don't get confused because like I spent a good 20 minutes or whatever talking about like the main distinction between Bayesian versus frequentist or supervised learning is with Bayesians, well, we're not solving optimization problems, we're solving integration problems, albeit indirectly by taking draws from the posterior distribution and criticizing, frequentist methods, supervised learning methods that just do optimization because you just get 1 point and no sense of the uncertainty for anything that comes out of it, including sort of predictions of future data. So what I'm saying is optimization is not a good way to estimate parameters of a model. Sampling is the correct way to estimate parameters in the model. But once we have posterior draws, we can use optimization on the output afterwards in order to make decisions or in order to like combine the predictions of different models in order to best predict future data or things like that. So the optimization comes after the estimation, and we use sampling from the posterior distribution in order to convey our uncertainty about the parameters conditional on the data, instead of just ignoring it, which is what most of supervised learning does, or by flipping it around, which is what frequentists do, and talk about the uncertainty of the estimator across data sets conditional on the parameters, when what we're doing and what actually makes sense is to talk about our uncertainty about the parameters conditional on the data that we have. So use sampling to estimate the model, and then where appropriate, do optimization on the output, rather than doing optimization in order to estimate the parameters in the first place and just sort of go with this. Because these points that solve the optimization problem are not necessarily, there's no transitivity of optimality. Just because they're sort of optimal with respect to a particular objective function that you define doesn't mean they're optimal for making predictions or making decisions or being optimal for any other objective function, utility function, or whatever that you're specifying. In order to find the expectation of that, you actually have to be pushing a whole posterior predictive distribution through the process. Anyway, that's what we have here, and then doing some optimization in order to choose the weights, in which case almost all of it got put on the more general smooth model where age was some not necessarily linear or quadratic, but just some smooth function relating it to the log rise. Questions? Okay, so we'll skip this because we're going to talk more about it on Thursday. Go to a new distribution, although we saw it implicitly on the poker homework problem. So the categorical distribution. Categorical distribution of observables over some sample space omega, that is the non-negative integers up to k, has a probability mass function given k probabilities, pi, such that those probabilities are non-negative and add up to 1. Well, the probability mass function for the so-called categorical distribution is just the product of each of those probabilities raised to an indicator function of whether x is equal to k. So for one of those, x is equal to k, and so the indicator function becomes 1, and you just have that pi k raised to the power of 1, which is pi k, or the indicator, I cannot say that today, indicator function, talking too much about integrals, the indicator function fails for all values of k that are not x, in which case you have a 0 in the exponent there, and you just have pi raised to the power of 0, which is 1. And so what this amounts to is the probability mass function is the kth probability when k is the same as x. So you can evaluate this probability mass function for any value of x that are integers between 1 and capital K. So the categorical distribution is a generalization of the Bernoulli, or Bernoulli is a special case where capital K is 2. But this is more general. It allows there to be k categories where k is greater than or equal to 2, of which exactly 1 gets chosen rather than merely like 1 failure and 1 success. To draw from it, you can just call sample like we did with bowling and poker and stuff like that, specifying size equal 1, and prob is equal to this vector of probabilities, which are non-negative and add up to 1. And if you want, and we'll see this in a second, you can make each of those probabilities a function of x's, coefficients, and all that. So that is the categorical distribution. It's actually extraordinarily simple, just barely more complicated than a Bernoulli, Bernoulli being a special case of categorical when k is equal to 2. And like the binomial can be thought of as the sum of a bunch of independent Bernoulli random variables, we can think of the multinomial distribution as the sum of a bunch of categorical random variables, each having the same vector of probabilities of occurring. So multinomial distribution is going to have a sample space of 0 up to n, and a probability mass function given here. There's like more factorial terms relative to the categorical distribution, and so multinomial distribution is analogous. It's a generalization of the binomial to the case where there are k possibilities, but also that you observe like n categoricals or the sum of n categoricals, and that gives you a multinomial distribution. So conversely, you can see the categorical as a special case of the multinomial when n is equal to 1, in which case you're just summing up one categorical. That would be the same as the multinomial. One point of clarification: the supervised learning people use categorical and multinomial, but in opposite ways. So what I just call categorical, the supervised learning people call multinomial, and what the supervised learning people call categorical, I call multinomial. The terminology I'm using comes from the older statistics literature, and the supervised learning people just like got it backwards. I mean, they use the right equations, they just switch the words on the distribution. So if you see someone talking about a categorical distribution and you're like, wait, no, that's a multinomial distribution, it's just they come from a computer science background rather than a statistics one. You can draw from a multinomial distribution in R using the R multinome, which is analogous to binome, has similar arguments, but again, the probability thing is going to be a vector. So let me click on that quickly and then go back to this. So how might we use this categorical distribution? Well, one of the models that is extraordinarily common to be seen estimated in like epidemiology is a so-called conditional logit model, which is sort of a stupid name because there's no such thing as an unconditional logit model. But the conditional logit model is different from a regular logit model, that both of which condition on predictors. And this conditional logit model, it's used often in epidemiology. It's also used a lot in microeconomics. Has been given the name Clogit, which is the thing that you type in Stata in order to estimate one of these models. And Stata was the first mainstream software that allowed you to estimate one of these things, and so it's sort of become known by its Stata name. Anyway, suppose you have J groups of people or whatever, and each group has n sub j members in the group. And suppose that within each group, there's going to be exactly one success, and consequently n sub j minus one failure. So someone a couple of years ago did his QMSS thesis using a Clogit model on like what happens in The Amazing Race. So that has like 12 people or whatever to start the season, and then each episode someone gets eliminated. So in this case, being eliminated would be considered success. Anyway, estimating a Clogit model for the evolution of what happens on like a reality show, but it comes up a lot in epidemiology and other things in the social sciences as well. So you can use your categorical distribution for the log likelihood of that, where the elements of the probability vector are going to be a function of predictors, in particular the so-called softmax transformation. And so within the jth group, you have what amounts to a linear predictor, which is like you take all of your x's and you multiply them by the respective coefficients to get eta. And then how do we transform eta into probabilities? Well, we use the softmax function given here, which is we just anti-log each of the etas and divide by the sum of that across the whole group. And now we'll get numbers that are between 0 and 1, and the probabilities add up to 1 across the group. And so this is appropriate when, by the design of the thing, there's going to be one success and everybody else does not succeed. Or it can be generalized to the case where you have more than one number of successes, as long as the number of successes is fixed rather than being a random variable. And so we can take the logarithm of the categorical PMF using the softmax transformation to map x's into probabilities, and we can estimate that in Stan. When we do take the logarithm of pi using Stan, we want to use again the log sub x function that you used on the homework in order to calculate the denominator in a numerically stable fashion. Also, because of the setup of one of these models, really you don't have likelihood contributions at the individual level. You just have likelihood contributions at the group level. Because within each group, by sort of the design of the data generating process, there's going to be one success and n sub j minus 1 failures. So once you've observed the one success, everyone else in that group has failed. And so that contributes no additional information. And so in the categorical distribution, it's basically just the logarithm of the probability for the one individual within each group that was successful, but that probability is going to involve the anti-log of the linear predictor terms for everyone in that group, including the n sub j minus 1 people who weren't successful. So we just have like j contributions to the likelihood coming from the log probability of success for the one person within each group who was actually successful. But in order to calculate that in a numerically stable fashion, we need to do log some x to obtain this denominator term. We don't have time to code that up in Stan today, but this is a model that can be estimated using Stan_Clojit in the rStanRm package. So here is a data set that comes from like one of the Stata documentation things. Most of the examples you can see involving a Clojit model come from people who are doing it in Stata. So this is a data set from the so-called high school and beyond experiment or whatever. It was a randomized experiment, and so some people got to put in like honors sort of classes with smaller class size and different syllabus and stuff like that, and others weren't. And the point of the high school and beyond project is to do pairing. So you'll see this often. They paired one person who was selected into the honors track or whatever with another person who was not. And they made those pairs in order for those two people to be as similar as possible on the background characteristics. And then there was some more randomization, and they studied outcomes like going forward a bunch of years or whatever. And so this are you in the honors composition class has this categorical structure. By the design of the high school and beyond experiment, one person in each pair was in the honors class, and the other person in the pair was in the regular class, even though they were sort of chosen in such a way to try to be as similar as possible on the observable characteristics. We can estimate a Clojit model to see how well they achieve that with respect to a few of the variables in the data set, namely the gender, race, and socioeconomic status of the students. So we call with Stan_Clojit, specify the data set. The additional argument that we have to specify in a Clojit model is called strata. In this case, it's the pair ID variable. So an indication as to which individual students are paired with which other student, one of which was in the honors class, another of which was not. And so then we can estimate the posterior distribution of these things, and just sort of eyeballing the medians, we can see that, there does seem to be some deviation by these, but it's fairly uncertain, or the posterior standard deviations are large. And so then we can, kind of evaluate, was the high school and beyond thing successful in sort of making pairs that don't have any systematic variation by gender, socioeconomic status, race. So we don't have time to go through the rest of that example today, but here's just another thing that you can do in rStanRm, and by getting the posterior distribution, you can do much better stuff with this than like estimating a model like that in Stata, or there's another R package where you can estimate the maximum likelihood version of this. But again, with the Bayesian approach, we get the uncertainty. Okay, out of time for today. Pick it up on Thursday. Talk about Bayes factors. Talk about prod spread, some other stuff, and then that'll be the last class before spring break.